Hi, in this video, we're going to take a look at diagnostic plots for linear regression models. All right, so after we build our model, we want to check and see, is this a good model? Is this a bad model? Do I need to go back and make some adjustments to improve my model? All right, so the most important thing that we can do for this is, first of all, our scatter plots. So right now, at this point in the class, we've only had one predictor variable, and we will always have one response variable, one target variable. So we just go ahead and plot that and take a look. When we get more predictor variables, we're going to need to go through and look at all the different scatter plots for predictor and target variables. So that the regular scatter plot is by far our most important tool in diagnosing the importance or the feasibility, the quality of our model. But after we do that, there's some other plots that give us further information that give us insight into what's going on, and it's easier to interpret specific aspects of what we want for a model. And so this example is taken from the textbook, A Modern Approach to Regression with R. And here is here's the website for the data set and the code. Now, I modified the code so that I feel like it's more informative, and I put in more plots, and I showed a technique on coloring your data points. All right, so let's go ahead and start doing the code part. So we're going to load the data, and to make things look better for the audience, I always put options to digits equals 2. That just reduces down the amount of input. Most of the time, if you have like 5 digits, are you, as a human, are you actually interpreting them? Probably not. Let's go ahead and read our data set in. And here, notice that I'm using the entire file path. I strongly recommend that you load your data using code in the same manner as I do. Don't do the point and click. When you start getting into more complicated projects, this is the better way to go. Now, something that is going on with the data set is that there is like an ID column in there. So I go ahead and just name all of the row. I go ahead and set the row names equal to that ID variable, just so that they match up, and that'll be more useful later down the road. And let's go ahead and take a look at our data. This is just the cable function knitter just prints the data out. And this isn't a large data set by any means. All right, the next thing I want to do is, since I'm going to be really focused on plots this go around, I want to color my data points in some way. Whenever I do a plot, I want to color those data points so that there's more information for me to pull out. All right, so what I'm going to do, I'm going to color my data points in a way that corresponds to the most important variable. Well, what's the most important variable? My target variable. So it's a good rule of thumb to color your scatter plots with the value of the target variable. And this can help like reveal a lot of things in your data if you choose to do this. I'm going to go ahead and use the Veridis Colors palette. And this is a very good palette for the colorblind. This puts color along the rainbow, intensity, and hue all on one continuous scale, and it's easier for us to interpret and interpret correctly. All right, so what I'm going to do, I'm going to take the number of rows of data that I have, and then I'm going to generate that many colors along the color palette. Now, what I need to do, I need to put those colors in the order of my target variable. All right, so what I'm going to do is I'm going to take the order of my target variable, which is runtime in this situation. So here is the order, and so it's going to be like 5, 6, 8, 2, something like that. It's going to say which row is the smallest value, then That's going to be the first number. Which row is the second smallest value? That'll be the second number. Which row is the third smallest, and so on. That's not quite what we want. This is we can think of this as a permutation from like abstract algebra or combinatorics. Well, I don't want the actual order. I want the inverse of the permutation that corresponds to the order. So what I'm going to do, I'm going to take from the matrix package inverse permutation, and I'm going to do the inverse permutation on the order that I get, and then I pass that to the color palette I just created, and that'll give it to me very nicely. All right, so let's go ahead and build the model, and we're going to take in a moment, we're going to look at those colors. All right, so for my model, I'm saying that runtime depends on run size, and I'm using production. And so in general, we want to use the linear model function. If you look through the textbook code, he uses frequently uses another way to do one predictor variable linear models. You know, I read through the help documentation. LM is generally the better way to go. It's also the way that you're going to be using it when you get into the more advanced stuff. All right, so let's go ahead and build a scatter plot. So remember, the basic scatter plot is our most important diagnostic for when we are building a model. So I go ahead and set X equal to run size, Y is run time. Now PCH, my plot character is 19. I'm telling R to give me a solid dot. If I don't, it's going to give me a circle. Open circle, which is open circle is very good when I have like big data, but when I have small data, a good solid dot is good. And then I'm going to go ahead and use the color that we already talked about to set up the what the color of the point is. And then after that, I'm going to go ahead and slap down the regression line. All right, so here's my model. And yeah, doesn't look too bad. Nothing really jumps out at me at this point. I mean, this might be a little bit low, but with such small data, it's hard to say. A good rule of thumb is if I could take a point and move it around, and moving that one point would not change my overall impression of the model, there's not really a whole lot to worry about. Okay, R gives us 4 default diagnostic plots. First one is residuals versus fitted. Second one is normal QQ plot. So you'll remember that from your introductory statistics course, you had to look at the normal QQ plot, or maybe a normal plot, QQ norm plot. It goes by many different names. You know, they put the dots along a line, and if it was really close to the line, you say it's normally distributed. Well, that's what we're doing here. Next one, the third is scale location, and third one is residual. The very last is residuals versus leverage. Now, how do we get these? Okay, so there's 4 plots. What will happen is if I just run the plot command as is, it's going to plot the first one, and then I click, it'll plot the second, replacing the first. Click, it'll plot the third, replacing the second, and then if I click again, it will replace the third and plot the fourth. Okay, that means that that's very good, it's very interactive, but I'm losing all those plots. So what I want to do instead, I'm using par for parameter, MF row. This tells R to go with 2 rows and 2 columns of plots. And that way I can get all 4 plots onto my screen at the same time. All right, so we've got the residuals versus fitted, normal QQ, scale location, and then residuals versus leverage. All right, so here is the fitted value. So this is what the model is saying the Y value will be, and here are the residuals. Now, I look here and I see that there's kind of like a pattern in the colors. All right, so whenever I see patterns in the colors, I need to pay attention to it. Well, let's think about this. Is that okay? Residuals versus fitted. I see that it's going along this route. Here is the fitted value. Well, yes, the colors, I define the colors to go along the y-axis. If we go back up here, I set the colors so that they get lighter as you go up. Well, the fitted value, if it's a good model, is going to be relatively close to the actual observed value. So I'm coloring by the observed value, which hopefully is correlated with the fitted value, the modeled value. So that's okay. I don't have any problems here. Now, here is the so this is standardized residuals. Here's a theoretical quantiles. All right, so if you went through and had to manually by hand compute QQ norm plots like I did when I went through introductory statistics, you probably remember how you had to line up and you had to set up the order of things. You had to figure out what was a likely value. I'm not going to make you do it. Be thankful for that. It was boring. I didn't get much out of it. But you notice that it's just a jumble of colors. That's okay. That's okay. Now, let's keep on going. We've got fitted value down here, and we can see that it goes along the colors. That's okay. And here's a square root of the standardized residuals, or square root of the absolute value. And then here we have leverage. And so leverage is going to correspond to how far from central tendency it is on the predictor variable. And here we have standardized residuals. All right, so remember, there are 3 types of residuals: regular residuals, standardized residuals, and studentized residuals. If I'm dealing in a lot of situations, all types of regression models will have residuals and standardized residuals. Studentized is only for regression. In general, if we want to work with studentized. They're the easiest to interpret. If we can't get that, then we go standardized. If we can't do that, we do just regular residuals. All right, so these are kind of zoomed in, kind of small, kind of hard to see. So I'm going to go ahead and replot these. Now here, I went ahead and I switched MF row to 1 by 1. So it's 1 row, 1 column for the subplots on the plot. Well, it's 1 row, 1 column, that's 1 plot. Therefore, I'm just plotting each time. So that I'm gonna have 4 different plots. And this is just the same code as previous. So let's take a look. Also, I want to follow this curve. Whenever it gives me a curve, what I'm trying to do, I'm trying to see, do I see a pattern on this? So if I saw like this red line going in like a angled line or curved up, here is staying pretty close to the middle, so I'm not too worried about it. Okay, I'm looking at my normal QQ plot. This is a little bit bumped up. That's kind of weird to see. Usually we focus on the left, the far left and the far right. That's usually where the most issues are. But honestly, I'm kind of feeling like this is probably not normally distributed, but it's probably going to be in the middle. There's probably going to be some issue there. All right, so I'll look along the curve. I don't see a pattern, so I'm okay. And the residuals versus leverage. So I've got leverage along the x-axis and standardized residuals along the y. And I don't really see like any kind of coherent pattern. So one thing it's going to do, it's going to find a curve for you to interpret. So just because there's a curve doesn't mean it's bad. Now, that was the 4 default plots. There's actually 2 more that we can also get. The other 2 deal with Cook's distance. So the ones that were not in the default are involving Cook's distance and Cook's distance versus leverage. So Cook's distance is just a measurement of how far the point is from like the rest of the data. So in this situation, I'm looking at 6 different plots. So here I chose to go 2 rows, 3 columns for my subplots. And so I've got Cook's distance in a bar plot format, and I have Cook's distance versus leverage. And this is pretty small, so it's hard to see what's going on. Now you'll notice that each time the 3 most extreme points are labeled. So by default, R goes with the 3 most extreme. Now that is, I can change that. I can change it so it doesn't flag any. I can set it so that it flags every single one. I have complete control over that. By default, it's 3. And I'm going to go ahead and just leave it as 3. So let's go ahead and find the Cook's distance plots. All right, so I've got a bar plot, and we can see that 9, 17, and 10 are the points with the largest Cook's distance. And you'll notice that since I colored the points in this manner, I declared what the color is. If I saw, like, let's say, all 3 of the flagged values were bright yellow or they were purple, then that would tip me off that there might be something else going on. There might be a deeper issue that I have to look at. There might be a connection between the points that are far off on Cook's distance and the extreme values for my target variable, and that might signal that a regular linear model might not fit this data very well. All right, so now here we've got leverage and Cook's distance. So leverage is a measurement of how much influence a point has on the overall model. I don't really see a pattern. All right, so the next thing I want to think about are the flagged points. So if I was to go through and I looked at all 6 plots, the observation 8, 9, 10, and 17 were the points that were flagged. Very frequently, you'll see the same numbers flagged every single time. So it's going to flag 3 points on every single plot, the 3 most extremes for the data. So what I'm going to do, I'm going to replot everything, and this time I'm going to color all the points black except observation 8, 9, 10, and 17. I'm going to plot those as red. If I see something that concerns me, I'm going to have to do something. I'm going to have to dig deeper. Maybe I'll have to omit the variable. I might have to replace the variable with another value through imputation. I might have to I might do nothing about it at all. So let's see. All right, so I can see the plot points. So these 4 points on the scatter plot are the lowest 3, like relative to the line where their model line is, and this is the highest. All right. So I mean, it's kind of not surprising that the ones that are kind of stretching away from the line are the ones that are getting flagged. All right, let's see. Looking here, I've got my 4 points. Yeah, these are like farther away from the rest, and these are the more extreme ones. Yep, their standardized residuals are farther away than the rest. Not surprising. They've got greater Cook's distance. Looking at this, I'm not actually worried about these 4 points. I would actually just go ahead and leave it as is and just accept it as being part of the model. I might, if I was able to, I might ask about those observations from the people who collected the data. But in general, I would just go ahead and leave it as is. Well, I hope you enjoyed this video. Take care. Goodbye.